All right, so in this problem, we're asked to find the equilibrium constant at 3 temperatures. And I have the strategy on the slide, but let's just kind of draw it out on paper as well. In order to get KEQ, the relationship there is between KEQ and standard free energy change. There's 2 ways to get standard free energy change. One of them is that standard free energy change equals enthalpy change minus temperature times standard entropy change. And to get the change in enthalpy and the change in entropy, we use that products minus reactants approach. There is also the other alternative way of finding standard free energy change by using the free energies of formations in that same products minus reactants approach. But the thing is that that only works for 298K, not for those non-standard temperatures. So I'm just going to do it the way that works for all 3 temperatures. So that means that we first need to find delta H and delta S. So starting with delta H, my standard enthalpy change is the sum of the coefficients of products times the enthalpies of formation of the products, standard, minus the same thing for the reactants, coefficients times standard enthalpy of formation for the reactants. So let's go ahead and do that. And I kind of rewrote my table in a, with my values for entropy and enthalpy right under each reactant product. That's the way I like to set it up. So for enthalpy, I do have a coefficient here and here. So on the 2 nitrogen compounds. So I need to make sure I do 2 times 33.2. That's my only product. And then for the reactants, 2 times 91 plus 0 equals negative 116 kilojoules per mole. So then the entropy change of the reaction, I'm not going to rewrite the equation for that, but it's kind of the same process as with enthalpy. So for our products, I've got 2 times 240, and then minus the reactants, I've got 2 times 211. Important to remember that entropies are usually given in joules per mole rather than kilojoules. So this one gives me minus 147 joules per mole Kelvin, which is the same as negative 0.147 kilojoules per mole Kelvin. And I think I'll actually round that to 0.15 kilojoules per mole. Okay, so I have my enthalpy and entropy change. So now I can work on my free energy. So for each temperature, I'm going to assume that my enthalpy and entropy changes are roughly the same, and it's just going to be a matter of substituting in the different temperatures. So for starting at 100 Kelvin, my enthalpy is minus 116.2 kilojoules per mole minus 100 Kelvin times negative 0.15 kilojoules per mole Kelvin. Those kelvins are going to cancel out. And so that's going to give me a value of minus 101.2 kilojoules per mole. I won't rewrite it for all the other ones, but let's just kind of, in your calculator, you can even just kind of re-enter the same equation, just substituting the different temperature. So for 298 Kelvin, the value for the free energy change, standard free energy change, ends up being negative 71.5. And for 400, ends up being minus 56.2 kilojoules per mole. So we can see all three of them are spontaneous. So two more questions we can ask here. One that kind of comes up is, well, at what temperature does this reaction become non-spontaneous? We can see that these free energies are getting smaller and smaller, or I should say maybe closer and closer to zero. And yeah, because the signs are the same on the enthalpy change and the entropy change, that does mean that there's some temperature at which this reaction becomes non-spontaneous. To figure that out, we can actually substitute in a 0 for that delta G term, because that's when the reaction becomes non-spontaneous, is when it has no free energy. So let's go ahead and calculate that. That wasn't actually part of this problem, but let's go ahead and do it anyway. If I substitute in a 0 for delta G, and my enthalpy is negative 116.2 minus, I'm going to use an X for the temperature, and negative 0.15 for the entropy, I can rearrange here just to solve for X. So I've got 116.2 equals, the negatives here cancel out, so I've got 0.15 times X. So I can actually solve for what temperature this reaction becomes non-spontaneous, and is 775 Kelvin. And any temperature above that. Okay. Now the last thing that was asked for in this problem were the equilibrium constants. So let's solve for them as well. My equation for the equilibrium constant is that KEQ equals e to the power of negative delta G over RT, and that's that standard free energy change. So again, I know my values for the delta G's, those ones that I just calculated up here. So I'll write it out for the first one. At 100 Kelvin, KEQ equals E to the negative 101.2. That's my delta G term, and I had to put a negative sign on that. So this is actually going to end up being a positive exponent, or a number greater than 1 when I take the exponential, divided by 0.00831 times 100. And when I do this out, I end up getting a very large number, 7.7 times 10 to the 32nd power. Oops. So that's my equilibrium constant for 100 degrees Kelvin. At 298, plugging in the same manner, I end up getting 5.6 times 10 to the 17th. And at 400, plugging in the same manner, I end up getting 1.7 times 10 to the negative, or to the positive 13. So what we can see here is that as temperatures are increasing, my equilibrium constant's actually getting smaller. And that makes sense, realizing that at some higher temperature, 775 Kelvin, this reaction actually becomes non-spontaneous, and higher than that will actually favor the reactant side, meaning that our KEQ would end up becoming a number smaller than 1. And does that make sense, just kind of thinking about the whole problem? Well, going back to when I solved for enthalpy, this negative value here tells me that this is an exothermic reaction. So looking all the way back to the equation, if I have an exothermic reaction, I like to think of that as essentially there's heat as a product of this reaction. And so if I'm raising the temperature of the reaction, it's like I'm putting more heat into the system. And from a sort of simplistic Le Chatelier's principle point of view, that means I'm kind of favoring the reactant side of the equilibrium system. So yeah, when I add that heat in, I'm favoring formation of the reactants. That's the same thing as being non-spontaneous as written, and it's the same thing as having an equilibrium constant less than 1. All right, I hope that was helpful. Hey guys, behind the scenes with Dr. Lesher here. Just because I know everyone's super curious, I wanted to show you my setup for making the videos of the problems. I have a very incredibly high-tech popcorn tin with my phone on top of it, weighted down by a can of Dole tropical fruit. Best thing is that after I'm done, I can open that popcorn tin and get some caramel corn that my grandmother and